So hello everyone, we're Team 9. My team name is rvpld, and our main focus is cutting down the FPGA compile time. So basically, hardware is ran on an FPGA and you're able to code and change things. But currently, it's on a dimension of time of hours to days. We would like to speed this time up to be more like hardware and take a couple of minutes. In order to do this, uh, Andrew will take over and explain.
Yeah, so some work has been done previously in this area, and what's been done is instead of compiling your code to one monolithic hardware block on the FPGA, instead break it up into separate discrete pieces that are located in physically different places on the FPGA, and then compiled where each one is essentially an individual operator and sends data between them through a network on the chip. And that way, if you change one of the code behind one of those operators, you just need to recompile the hardware for that operator and can still interface with the rest of the operators in the same way. Our goal is to speed it up even further by taking some of these hardware sections and changing them into RISC-V software CPUs. We call those leaves. And then we can use those softcore CPUs to run the same tasks as the hardware operators, but actually just run them as software on the soft cores. And then when you make a change to one of those, the code behind one of those operators, you just need to recompile your software for that RISC-V core.
So we've sort of split the project up into two distinct parts. We have sort of the control, what we're calling the controller side and the leaf side, as Andrew mentioned. So on the controller side, we essentially want to build off of this previous work that used the Zinc processor system, which restricts the system to using very specific smaller devices than what we want to eventually target. And so we want to have an open source drop-in replacement for the Zinc processor as a way of setting up the network on chip and streaming data in and out of the accelerator. And so we're using a SoC generator called LightX, which builds off of Python to take a description of the SoC and use a bunch of library components to build a system on chip that has a processor and a DRAM controller and UART interfaces and all the sort of stuff that consists of a network of a system on chip. And so our current status, we've taken this core system on chip and we have added the ability to control the network on chip over an Axi-Lite bus that was already a part of the system on chip to communicate with peripherals. And we've also added additional interfaces to the DRAM controller in order to stream data with DMA in and out of the accelerator. And so, we've sort of reached the point where this can be a drop-in replacement for the Zinc processing system. But we still, in the future, we need to work on actually, integrating this with the Leaf work and, ensuring that it works in all of the correct cases with the network on chip and with these other accelerators. So then I'll pass it off to Matthew to talk about the progress on the Leaf side.
So on the Leaf side, we sort of have two different aspects we're working on. One aspect is that we need to be able to compile code to run on these leaves. And from that perspective, we have been able to modify a RISC-V toolchain to be able to compile to these leaves, particularly with an additional custom instruction for RISC-V soft cores that allow our cores to stream in and stream out data. And then we also need to write an implementation for these cores that can stream in and stream out. So the implementation is almost done. However, there still needs to be some work, and our goals for next semester are to finish off that implementation and then start integrating with the controller and with the network on chip.
Thank you.